Welcome to my talk for the Nearly Carbon Neutral Geometric Topology Conference. First, I would like to thank all the organizers for organizing this and for giving me the opportunity to speak in this conference. I think it's a really great idea. So today I'm going to talk about proper actions on the symplectic group and its Lie algebra, mostly on the Lie algebra actually. I'll say a few words about the symplectic group at the end. So what I'll talk about is joint work with Fanny Kessel, who is at IHES. So let's get started. First, I'll define what a flat affine structure on a manifold is for those who don't know. So when you have a manifold, you have an atlas of charts. If you ask that these charts be such that the transition maps are locally affine transformations, so restrictions of elements of the affine group, which you can write as a semi-direct product, then you say that the manifold is equipped with an affine structure. Equivalently, you can just give an affine connection on your manifold, on your smooth manifold, and if it's torsion-free and the curvature is 0, then that is the same data as a flat affine structure, it turns out. So the first type of example you might think of is if you have a discrete subgroup of affine transformations which acts properly on Rn, then the quotient automatically has a flat affine structure. And the structures that arise from this construction are called complete. And it turns out that this is the same as asking that the flat connection be geodesically complete, which is a natural condition you might want to put on your flat affine manifolds. So when you study these complete flat affine manifolds, it turns out you're studying actually just actions of discrete groups on Rn by affine transformations. So an affine action of a discrete group is determined by two pieces of data. First, you need a homomorphism, which is called the linear part, into GLN. And in general, whenever you have a representation of a group into another group, or a homomorphism from a group into a semi-direct product, then it separates into these two pieces, a homomorphism and a cocycle. So the translational part is not a homomorphism. It's like a twisted homomorphism. So it satisfies this cocycle condition. When we have a pair, rho homomorphism into GLNR and U cocycle into Rn, then we will denote by rho U the homomorphism which goes into the space of affine transformations of Rn and is defined by this pair rho and U. So easy examples of proper affine actions on the two-dimensional plane are given by these two pictures you see here. So here on the left, you have the standard tiling of R2 by squares, where you have two translations, and you just take the group generated by these two linearly independent translations. And on the right, this is a different, more exotic type of proper affine action. The group is still Z2, so free abelian group on two generators. But now the affine transformations will act on this tiling by permuting the tiles again. And now this is a tiling by parabolas. And the transformations have linear part which is a shear. So the motivation for this talk is going to be, well, what can we say about these proper affine actions on Rn? Or equivalently, can we classify complete flat affine manifolds? So let's see what's some of the things that are known about this problem. So first, there's actions of virtually solvable groups. So the pictures on the previous slide were examples of this type. In some sense, these groups are the simple, easy kind to understand, and they're very well understood because they live inside Lie groups, which themselves act properly on Rn affinely, and so you can just study those, and that's sort of easy. So in the 70s, Milner asked a question which was inspired by the Auslander conjecture, which is, are those all of the examples? If you have a discrete group which acts properly on Rn by affine transformations, is it virtually a solvable group? And it turns out that this was not true. Sort of surprising result. So counterexamples were constructed by Margulis of non-abelian free groups acting properly and affinely on R3. So for the rest of the talk, we'll be interested in sort of generalizations of this Margulis result. And so we will assume that all of our discrete groups are non-virtually solvable. And since we're only talking about linear groups here, that is, groups that admit a faithful linear representation, then the TITS alternative tells us that these groups, if they're not virtually solvable, then they must contain, as a subgroup, some non-abelian free group, or if you want, a free group on two generators. So there's a lot of work that's been put into understanding these affine actions, and in dimension 3 we now have a pretty complete picture of what happens, which I will quickly describe some of the features of. So Fried and Goldman in 1983 showed that if you have a proper action of one of these non-virtually solvable groups, then the linear part itself, just the row, is discrete itself and contained in the identity component of SO21. And all discrete subgroups of SO21 are pretty well understood. They act properly on the hyperbolic plane, preserving orientation, because this is the isometry group of the orientation-preserving isometry group of the hyperbolic plane. And so you know that what you're dealing with as the linear part is the holonomy representation of a hyperbolic surface. So knowing this, it turns out that there's another way of seeing these affine actions, because the Lie algebra of SO21, or you might want to think of as of SL2R instead of SO21 if you like 2x2 matrices instead of 3x3 matrices. Its Lie algebra is three-dimensional, and it comes equipped with the killing form, which has signature 2-1. So the linear action of SL2R by the adjoint representation on its Lie algebra is the same as the linear action of SO21 on R3. So when you're thinking of these affine transformations which are contained in SO21, you might as well be thinking of the group PSL2R acting by the adjoint representation on its Lie algebra and then some translation part. So our vector space is going to be the Lie algebra of SL2R for what's coming next. So when you do this, you get a new interpretation for cocycles. So a row cocycle, U, you can also think of it as a tangent vector to the space of homomorphisms from your group into PSL2R at the representation row. It turns out that by a pretty simple calculation, you can show that if you have a path of representations and you take its derivative at t equals 0, the object you get has this cocycle condition, the same one I talked about earlier when defining affine representations. So you can think of a row cocycle U as both the translational part of some representation into the affine group, or as a tangent vector to the space of representations. So the key insight or theorem is that informally, if you have a proper affine action on R3, so the sort of in this first part of the sentence, I'm thinking of the first interpretation of cocycles, the translational part of some affine action, then this affine action is proper precisely when the corresponding tangent vector to the representation variety is a uniformly lengthening direction. So you think of the point rho as the holonomy of some hyperbolic structure where you're sitting at, and then you point in some direction, that's the tangent vector, u, then this u will, together with rho, define a proper affine action on the Lie algebra SL2R precisely when this direction is a deformation direction of hyperbolic structure where everything is getting longer. So all the closed geodesics are getting uniformly longer. And I will make a more precise statement. So if you write L for the hyperbolic translation length, then you can write the theorem this way. If you have the linear holonomy of a complete hyperbolic structure, and you have a rho cocycle, then you have a proper action on SL2R by this pair rho u, if and only if this quantity is positive, the infimum of this derivative. So on the bottom, this is just the translation length of the element rho, and on the top, you should think of this part here as a path of representations, or actually just a path of elements. So you have rho of gamma, which is some element in SL2R, then you multiply it on the left by some path of elements that goes through the identity. So all of this together is a path in the group PSL2R, which at t equals 0 goes through rho of gamma, and whose tangent vector corresponds to u of gamma. So if you measure the variation of the length, so d by dt at t equals 0 of this, divided by the length itself, this should be uniformly bigger than 0. And actually, slight caveat, you might want to replace u by minus u. So if instead of being uniformly lengthening, the cocycle were uniformly shortening, this would also be corresponding to a proper affine action. So if you multiply a cocycle by any scalar multiple, actually, including negative ones, it preserves the properness of the action. So it might be that you need to flip the sign. So as a corollary, if you have the fundamental group of a closed hyperbolic surface, then you cannot find any proper affine action on the Lie algebra SL2R. This is essentially because whenever you have a closed geodesic on a hyperbolic surface, the Collar lemma tells you that if it gets longer, some other closed geodesic has to get shorter. So you cannot have uniform lengthening. So how do you, in practice, construct these lengthening cocycles? So I'll be thinking of the fundamental group of a surface, of an infinite area surface, or a convex co-compact, if you like. So for instance, you could think of this as the Poincaré disk, and then these two green lines are geodesics, the two blue lines are geodesics, and they should be identified by elements in PSL2R. I want to build a path of holonomies of hyperbolic structures, or a path of representations, so that every geodesic becomes longer. Or maybe, to begin with, let's start by making some geodesics longer. So if I do this, by which I mean I replace the blue geodesics by the red geodesics, and I have a new element which, instead of identifying blue with blue, identifies red with red now. My two generators for the discrete group that I'll be looking at will be the same one from before, which identifies the two green geodesics, and replace the one which identified the two blue geodesics by a one that identifies the two red geodesics. So this one will have a longer translation length because the geodesics are further apart. So actually, if we did this to both, so if we did the same thing with the green generator, then we would get that every geodesic becomes longer. That's a theorem, it's not obvious. And so the idea is to insert these strips. You take a geodesic, which is infinite, in your hyperbolic surface. So here, the blue geodesic sort of goes from one boundary component back to a boundary component and out to infinity. And you insert some strip here to make all the geodesics that cross this blue geodesic will now have to become longer by this much. And if you do this infinitesimally, so make the red geodesic closer and closer to the blue one to get a path of representations, then the derivative to this path will be a proper cocycle, or a cocycle which defines a proper affine action. So these types of deformations are called strip deformations, and they were introduced by Thurston, I believe, but then this application is by Denziger, Guerrito, and Cassel. So an infinitesimal strip deformation along enough pairwise non-homotopic arcs gives a proper affine deformation. So this is what I sort of informally said in the previous slide. Actually, every proper affine deformation of a hyperbolic surface can be obtained this way. So strip deformations give you everything in dimension 3. And the space of proper affine deformations with a fixed linear part, you can naturally parameterize it by an open subcomplex of the arc complex. So the arc complex is a simplicial complex where the simplices are given by collections of pairwise non-homotopic arcs. And so having a sufficiently large collection is the condition which defines the open subcomplex. So maybe you want to see what these examples of proper affine actions on R3 look like. So perhaps I'll show a little interactive demonstration made in Mathematica. So this is a tiling of R3 by a group of affine transformations. So a fundamental domain is the region between the three surfaces which you see here. These surfaces are called crooked planes. They were introduced by Todd Drum, a good friend who very sadly passed away last March. So you can use these crooked planes in order to cut up a fundamental domain for these proper affine actions. So here, this is an action of a Coxeter group, so 3 involutions which have no relation between them. So any composition of a pair of involutions has infinite order. If you want to understand what's going on a little bit more in this picture, what I can do is glue back up all of these crooked planes together. And if you look at this picture from the top, you can see the familiar tiling of the hyperbolic plane, this sort of limit circle you see here, by triangles, ideal triangles. So this is an ideal triangle, and then you have 3 stuck to it on each side, and then 2 more on each of those. So this would be the linear action only. If there were no translational parts, if there's no cocycle, then the linear action looks like this. And if you add some small cocycle, so add some translational part, then these surfaces they come apart and they become disjoint. Then you could use the ping pong lemma to prove that this is actually a free product of Z2s. And you can see the orbit of each of the 3 crooked planes here. You can convince yourself that they're all disjoint, and it's actually a non-trivial theorem that they fill up all of R3.